Hey guys, what's up? Welcome to another chemistry basics video with me, Hunter Koloje, and this one will be on metallic bonding. So the first thing you need to know about everything metallic is that all these properties are going to be based on the sea of electrons. So what the sea of electron is, or the easiest way to imagine it, is a bunch of positively charged nuclei surrounded by a sea of negative charge or free-floating electrons. And so why this happens is because transition metals, not group 1 or 2 metals, have these d orbitals, right? And these d orbitals have many unpaired or free-floating electrons that allow for these metals to have many different properties that are very characteristic of metals, many of which you probably never even thought were because of delocalized electrons or anything like that. So these four main properties of metal that are easily identifiable because of the sea of electrons are delocalized electrons are malleability, conductivity, ductility, and low volatility. So first we've got malleability, which is the ability of this metal to be hammered out and spread thin so that these atoms are not stacked on top of each other but just spread thin. This is easy to imagine because if you have a sea of electrons with free-floating electrons that slide past each other regularly, simply hammering on them won't break them. They'll just slide past each other and form this sheet, very characteristic of metallic bonding. And what you have in this picture is gold leaf foil or gold foil. And this is because gold is very malleable, one of the most malleable metals. So next we have conductivity, or the ability of a metal to conduct electricity, but also to conduct heat. Many people forget that. And the greatest reason that metal is able to conduct heat is because the flow of electricity is just the flow of electrons, and given that there are many free-floating electrons in a metal, it is just naturally prone to conduct electricity. And the reason it conducts heat so well is because these free-floating ions are able to hold heat energy and then transfer it to the next one, and they are able to just transfer it down a line so that the heat energy is dispersed. Next we have ductility, or the ability of this metal to be spread thin into a wire. Also very characteristic of metal. If you've ever stripped a wire, like in the conductivity photo right here, you will almost always see copper or some other metal in there. And the reason for this is because, just like malleability, the metals are able to be spread thin without breaking. So if you were to try and spread something like, I don't know, carbon into a thin wire, if you had solid carbon, it would most likely not work. Just think of something like trying to stretch graphite into a thin wire, probably wouldn't work. It would snap before it could reach the point of ductility that copper or nickel or something could reach. And next we have low volatility. Low volatility means that these metals have very, very high melting points. And you might think, well, that doesn't really seem characteristic of a metal in my head because of the fact that these metallic bonds kind of seem unorganized. But the fact that there's a huge body of negative charge with tons of positively charged nuclei in the middle creates this huge force of attraction. And think of trying to melt that down or break that bond, it was going to take a lot of energy. So you can kind of imagine these trends on the periodic table using the sea of electrons model, but ultimately, if you want to predict the trends as you move across the transition metals in the periodic table, you are going to need the shell model. And so you might think as you go across the periodic table from left to right like so, sorry it's vertical here, that as you add electrons, you are going to gains in something like boiling point. Your boiling point is going to go up, but that is actually the opposite of the fact. Boiling point kind of peaks around here, and then as you go down, it just starts to drop. And this is because as you start pairing electrons in the d orbital, like you can see here, these electrons are by themselves here, and then they start getting paired. Then these metals are losing these free-floating electrons in the sea of electrons. And that's actually bad for transition metals in terms of increased boiling point and other things, because as these electrons are tied down, married to one another, without being able to slide past, the boiling point will actually decrease instead of increase. And same goes with ductility and malleability, it's less so and less so. So not only do they have properties like conductivity and stuff like that, but metals are also able to form, or transition metals are also able to form alloys, as well as have a few other properties here and there. So what an alloy is an alloy is when you have one metal, and there are basically two forms, interstitial and substitutional. So interstitial alloys are something like you see in this bottom right graphic here, where the holes in between this previous metal are filled with other metals, sometimes can even be done with carbon to form high carbon steel. And this couldn't be done with most solids, but the fact that metal is able to be stretched and formed at its own free will, and it's very free moving, though it is a solid, makes it so that you can fill these holes. Substitutional is when you replace atoms, much like here, with other atoms, and this is to create a metal like brass, oftentimes very soft, very malleable, but interstitial, an example would be steel, and this is for making something super, super strong. And ultimately, guys, I'm no expert on metallic bonding, so when in doubt, just remember, watch the Mr. Anderson video.